Hello there, and welcome back to the Sleep Science. Tonight you drift into a stage that is everywhere yet nowhere, a vast invisible fabric cradling every step you take and every breath you draw. Imagine lying back beneath the night sky, the stars scattered like glowing crumbs on an endless dark tablecloth. You think you're gazing into emptiness, but what surrounds you is not a void at all, it's the space-time, the quiet theatre that makes existence possible. It feels solid underfoot though you never touch it. It hums around you though you never hear it. You probably won't survive this trip if you expect neat answers, because physicists still debate what space-time really is. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And I'd love it if you posted your location and your local time in the comments, so we can build our own sleepy constellation of listeners across the globe. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You picture yourself standing in a quiet field, moonlight painting the grass silver. You reach out as if you could press your palm against the unseen fabric beneath your feet. In a way you can, every second you remain upright. It's this fabric that holds you in place, balancing you against the downward tug of Earth. Without space-time, there'd be no down to fall toward and no up to resist it. You're not just living on Earth, you're woven into the tapestry itself. Centuries ago, people assumed space was simply an empty box, an infinite container where planets hung like ornaments. Newton gave that box rules. Absolute space, absolute time, both steady and dependable, like the ticking of a clock in a royal hall. Drop an apple, measure the fall, and you think you've mastered the whole stage. The quirky part? Some philosophers in Newton's own day whispered doubts, suggesting maybe space and time weren't things at all, but just convenient bookkeeping. Historians still argue whether Newton himself believed in a physical space, or if he merely used the idea as a practical scaffold for his math. Fast forward to Einstein, who strolls into the story with hair like he just fought a thundercloud. He insists the box is not fixed, it stretches, curves, and even flows with the passage of events. Suddenly, you're not standing on neutral ground but floating on something alive, reactive, and occasionally mischievous. If a massive planet saunters by, space-time bows politely beneath it. If you try to race a beam of light, space-time smirks and slows your clocks until you stumble, baffled. Here's a quirky thought. Some ancient cultures imagined the cosmos as a great animal skin stretched tight across wooden posts. When the wind blew, the skin trembled and the stars quivered. You can almost see how that metaphor survives in our modern idea of space-time as a stretched sheet. Of course, physicists would grumble that it's not literally a fabric, you won't snag it with your car keys, but the comparison helps your sleepy mind picture something otherwise too slippery to grasp. As you walk in this mental field, you feel the weight of history pressing gently on your shoulders. Think of Galileo dropping spheres from the Leaning Tower of Pisa. Maybe he did, maybe he didn't. Historians still argue whether the experiment actually happened or was just a teaching story. Either way, the image of falling objects is what led us toward the modern view. Gravity isn't a force pulling apples downward, but the ground itself sliding towards the apple along the slope of space-time. You and the fruit are both caught in the same invisible river. You glance upward, where satellites orbit, and you realize their clocks tick at a slightly different pace than yours. Thanks to this restless stage, your phone's GPS corrects for it every day, quietly proving space-time's existence every time you find the nearest taco stand. Imagine explaining that to Newton. Sir, my handheld rectangle relies on the geometry of space-time to tell me where I parked. He might nod politely, then faint. The beauty of this fabric is how it lets you exist in two modes at once. You're a dreamer floating on abstractions, and you're a body pressing real weight into the earth. Space-time doesn't care if you understand it. It holds you just the same. The playful part is realizing you can never step outside it to peek at the loom. You're both weaver and thread, a participant in the mystery. And so, as the night deepens, you take another slow breath and let your shoulders sink. You picture the stars above as pins stuck through the fabric, each galaxy tugging a little at the weave. Somewhere far away, space-time swells outward, carrying everything along like raisins in rising bread dough. Somewhere closer, in the microsecond tick of your watch, space-time slips quietly forward, keeping the rhythm that lets you call this moment now. You don't need to solve it tonight. Just know that the invisible floor beneath your feet is less like a carpet and more like an ocean tide, endlessly patient, endlessly shifting, and always ready to catch you. You keep drifting, letting the imagery settle like mist across your thoughts, and soon you find yourself standing in the middle of a grand hallway lined with portraits. Each frame holds a thinker staring back at you. Stern Newton with powdered wig, dreamy Einstein with mischievous eyes, and countless others whose names get less recognition on high school posters. Their gazes are silent arguments about what space and time really mean. And you realize you've stumbled into the long corridor of physics history. For centuries, people believed in Newton's absolute space and absolute time. Picture it as a giant, unchanging grid, a universal backdrop that didn't care what was happening inside it. An apple falls? Fine. A comet soars? Sure. The grid itself stays perfectly still like graph paper stretching to infinity. Newton gave this structure mathematical dignity, letting scientists measure motions, forces, and orbits with clockwork precision. His system was so effective that for 200 years, hardly anyone bothered to challenge it. After all, if the apple reliably bonked you on the head, who cared about unseen fabric? But then cracks appeared. Think of Michelson and Morley in the 1880s, setting up their finicky mirrors to catch the ether wind. Back then, physicists thought light waves had to ripple through some medium, just as sound needs air. The idea was that Earth must be ploughing through this cosmic ether, creating a detectable breeze of sorts. They tested for it, expecting subtle shifts in the interference pattern. Result? Nothing. No ether. The universe gave them the scientific equivalent of a shrug. To this day, historians still argue whether their null result shocked the community instantly, or if it took decades to truly sink in. Enter Einstein, walking lightly but leaving heavy footprints. He proposed that maybe space and time weren't absolute after all. They could flex. They could adjust themselves so that the speed of light always came out the same, no matter how fast you moved. That idea seems simple when whispered in the dark, but it flips centuries of assumptions. Suddenly time is not the same for everyone. Space isn't either. What you measure depends on how you're moving. It's as if the hallway of portraits you're wandering through stretches or compresses as you walk faster, tricking you into wondering whether you're late or early to your own bedtime. A quirky side note, when Einstein published Special Relativity in 1905, he was still working at the Swiss Patent Office. Imagine filing paperwork for someone's new kind of toaster, then scribbling equations on your lunch break that rewrite the laws of the cosmos. Colleagues said he often muttered to himself about moving trains and clocks, which is probably not the office chatter HR was expecting. Meanwhile, Newton's loyalists weren't ready to let go. They argued that Einstein's proposals were just mathematical conveniences. Maybe deep down, absolute space and time still lurked, hidden beneath the equations. Historians still argue whether Einstein himself considered spacetime a physical substance or just an elegant map of events. That debate continues even now, tucked away in conference rooms where coffee flows faster than consensus. You, pacing slowly down this imaginary hallway, feel the tension between those two visions. In Newton's world, you could set one cosmic clock and trust it forever. In Einstein's world, every traveller carries their own clock, and they don't always agree. The unsettling part is that both visions work in their own domains. Newton still guides your car's suspension and your grocery cart's squeaky wheel. Einstein steps in only when speed soars or gravity deepens. It's like keeping both a ruler and a flexible tape measure. You use whichever fits the job. Think of Galileo again, sketching his inclined planes centuries earlier. He gave us the first hints that time might not be as simple as church bells chiming in unison. Some accounts say he even timed falling objects by listening to the beats of his own pulse. Whether he did or not, historians still argue, but it makes for a good bedtime image. A man holding his wrist, squinting at wooden ramps, trying to hear time itself through his veins. And here you are, centuries later, with a glowing phone that quietly relies on Einstein's corrections to Newton's laws every single day. Satellites overhead tick a little differently than clocks on Earth, and your map app silently merges both visions so you don't get lost. That merger is what spacetime really is, an uneasy peace treaty between the old grid and the new flexible fabric. As you continue down the hallway of portraits, the air feels thicker, as though the very walls bend around you. It's a gentle reminder that history is not static. Our ideas about space and time shift just like the fabric itself, reshaped by experiment, by imagination, and sometimes by sheer stubbornness. You keep walking, and you realize you're not just tracing old footsteps, you're stretching space-time with every sleepy stride. You pause in the hallway, tilting your head as if listening for some faint hum beyond the portraits. There it is, the constant whisper of light, the ultimate speed limit written into space-time itself. No matter how hard you push, no matter how much caffeine you pour into your rocket engines, you can't outrun it. Light zips along at nearly 300,000 kilometers per second, and space-time seems to bow down to this number, as though it were royalty. You could say that light wears the crown. And everything else, the planets, your sneakers, even your midnight snacks, falls in line behind its rule. This constancy was the puzzle that tripped up Newton's tidy world. If light always moves at the same speed, then your measurements of space and time have to flex to keep the books balanced. Imagine two travellers, you on your sleepy bicycle ride through town and a friend zooming past in a rocket. If you both shine a flashlight, you'll each measure the beam moving at exactly the same speed. Even though one of you is pedaling like a turtle and the other is blasting like a comet, how can that be? The answer is both absurd and beautiful. Space-time bends the rules of measurement to make sure the number stays fixed. Distances stretch, clocks tick differently, and your common sense sulks in a corner. Here's a historical tidbit. In 1676, Danish astronomer Ole Rømer first estimated the speed of light by studying the eclipses of Jupiter's moon Io. He noticed the timing shifted depending on Earth's position in its orbit, suggesting light had a finite speed. That was a revolutionary thought in a world where many assumed light travelled instantaneously, like a divine thought crossing the heavens. Historians still argue whether his colleagues truly believed him at first, or politely nodded and went back to polishing their telescopes. On the quirky side, some 19th century thinkers imagined light as little particles riding invisible gears of an ether machine, as if the cosmos were a gigantic Victorian clock. One even sketched diagrams where light beams were literal corkscrews drilling through space. Charming, yes. Accurate, not so much. For you, though, the real punchline is how this cosmic speed limit infiltrates daily life. Every video call you make, every ping in a multiplayer game, every satellite signal beaming GPS coordinates, all of them are subject to light's stubborn pace. You've probably cursed your Wi-Fi lag without realizing you were actually bumping up against a fundamental law of the universe. Blame Einstein, or maybe just shrug and order pizza instead. Thinking about this, if you tried to chase a light beam, no matter how close you thought you got, it would always streak away at the same speed. That realization is what made Einstein scratch his head and eventually redraw the universe. He imagined being a kid riding alongside a ray of light. What would it look like if you caught up? Spoiler, you can't. The rules of space-time say no, and that childhood musing is what blossomed into special relativity. You wander deeper into the corridor, and the air around you seems to shimmer, as if light itself is painting your path. The walls bend ever so slightly, reminding you that keeping light constant requires space and time to contort themselves. If your rocket friend's clock runs slower than yours, don't worry. That's just space-time doing its accounting tricks to keep the speed limit consistent. Here's a fun little brain tickler. If you hop on a spaceship and head off near light speed, your snacks will stay fresh longer relative to Earth. Time slows down for you. Imagine coming back to discover your favourite TV show has already run for 30 seasons while you're still nibbling on episode 3. Historians still argue whether Einstein's contemporaries truly grasped how radical this was, or if they dismissed it as a clever but irrelevant bit of math. Either way, your interstellar Netflix queue is doomed. Light doesn't just tell you how fast you can go, it defines what's possible at all. Communication, causality, memory, all tethered to that limit. Without it, the universe might unravel into paradoxes, like receiving a text from yourself before you've sent it. Quirky as it sounds, physicists sometimes debate whether faster-than-light particles, tachyons, could exist. Most dismiss them as imaginary math gremlins, but they remain a reminder that space-time still holds secrets. And as you drift onward, lulled by the idea of this untouchable speed, you realise the true comfort in it. The universe has boundaries. Not cruel walls, but gentle guide rails. You can dream about racing photons, but you can also rest easy, knowing space-time won't let you shatter its order. Like a kindly parent tucking you in, it whispers, "You can go anywhere, but not faster than this." You wander out of the glowing corridor of light and step into a quieter landscape, one where clocks tick in peculiar rhythms. It's as though you've stumbled into a field of tall grass, but instead of blades swaying in the breeze, each stalk is a shimmering clock face. Some dials whirl quickly, others crawl, and together they remind you that time is not the steady march you once believed. It bends, it stretches, and it sulks when you move too fast or climb too high. Welcome to the strange world of time dilation. The rule is simple enough: the faster you move, the slower your clock runs compared to someone at rest. And the stronger the gravity around you, the slower your clock ticks compared to someone farther away. Yet simple here is like describing a croissant as bread. You might nod politely, but inside you're thinking, this is layered, buttery madness. Consider the global positioning system, the quiet hero of your late-night snack runs. Those satellites circling overhead carry atomic clocks that are slightly out of sync with the ones on Earth. Why? Because they're moving quickly and hovering in weaker gravity, so both speed and altitude twist their sense of time. Engineers have to correct for it, otherwise your GPS would drift by kilometers each day. Imagine trying to find your local coffee shop and winding up in a swamp instead. Time dilation, inconvenient but also life-saving for your navigation. A historical anchor here. In 1971, scientists actually tested this effect with commercial airliners. They flew atomic clocks around the world on passenger planes, complete with coffee, peanuts, and probably annoyed seatmates, and compared them with identical clocks left behind. The results? Tiny but measurable differences, exactly as Einstein predicted. Historians still argue whether the experiment was truly decisive or more of a charming confirmation, but either way, it made time dilation feel far less like a theoretical parlour trick, and more like a cosmic prank playing out in coach class. On the quirky side, you might be amused to learn that astronauts aboard the International Space Station technically age just a bit slower than you. They're moving fast, so their personal clocks tick more leisurely, but at the same time they're closer to Earth's gravity, which pulls time back the other way. The net result is that they return to Earth younger by a fraction of a second compared to their Earthbound twins. So if you want the ultimate anti-aging treatment, forget face cream, just book a long-term stay in low Earth orbit. Side effects may include zero-gravity hiccups and floating crumbs in your hair. You stroll among the field of clocks, noticing how each one seems tied to an invisible cord that runs into the sky. You picture the clocks aboard satellites tugged by lighter gravity, drifting just a bit quicker than yours. You picture the watches strapped to astronauts' wrists, slipping ever so slightly behind. You picture your own humble kitchen clock stubbornly ticking at Earth's ground level, and you feel the odd comfort of being part of this grand orchestra of mismatched beats. It gets stranger. If you were to park yourself near a black hole, time for you would drag painfully slow. Someone far away could watch entire civilizations rise and fall while you are still sipping your tea. This isn't science fiction, it's baked into the geometry of space-time. Historians still argue whether Einstein ever truly grasped how extreme this effect could be near singularities, or whether that insight blossomed only later through his successors. Either way, it's a chilling reminder that time itself is elastic, stretching like cosmic taffy under the right conditions. And yet, you experience hints of this every day. Your phone quietly accounts for it. Jet-lag toys with your personal sense of time, though that's just biology acting cranky. Even your heart has its own rhythm, not quite in sync with the world around it. Time dilation is everywhere. You just rarely notice it because you and your surroundings tend to stretch together. It's like dancing in a crowd. You don't realize you're moving until the music suddenly changes. You pause, staring at one shimmering clock that ticks just a hair slower than its neighbors. You imagine yourself boarding a rocket, heading off at near light speed, and returning to Earth to find your friends older, your favorite TV series completed, and your neighborhood replaced by arcades run by robots. You laugh softly at the absurdity, then sigh at the poignancy. The universe lets you travel through space, but the toll is always time. And in that sigh you feel the sleepy tug of space-time itself. You don't need to fly a rocket to sense it. You just need to notice that the very seconds you're living right now are not quite the same as someone else's, drifting in their own corner of the cosmos. The fabric holds you both, patiently stretching to keep light constant, quietly skewing the clock so the story still makes sense. You leave behind the meadow of shimmering clocks and step into a landscape that feels more solid underfoot, though the ground undulates softly, like the padded floor of a trampoline. Every step you take sinks ever so slightly, and you realize that this is how space-time reveals gravity. not as an invisible pull, but as a gentle sagging beneath your weight. The old idea of gravity as a force yanking apples downward gets replaced here by something subtler. Mass tells space-time how to curve, and curved space-time tells you how to move. It's a simple slogan, really, Einstein's neat summary of general relativity, but as you wander, it becomes vivid. Imagine tossing a marble across this trampoline surface. It doesn't shoot off in a straight line. Instead, it loops around a heavier ball resting in the centre. That's orbit in action. Earth curves the fabric, and the moon rolls endlessly along the slope. No invisible hand drags it down. It's just space-time bending the path. Historically, this leap was massive. In 1919, during a solar eclipse, Arthur Eddington led expeditions to test Einstein's prediction that light would bend around the sun. Observers on Príncipe Island and in Brazil photographed starlight appearing shifted, as if space itself were warped by the sun's presence. The newspapers ran headlines proclaiming Newton's fall and Einstein's triumph. Historians still argue whether the data were truly conclusive or massaged a little to fit the theory, but the symbolic victory stuck. Overnight, Einstein went from patent clerk philosopher to global celebrity. A quirky fact, Einstein wasn't actually thrilled about the press frenzy. He once grumbled that every coachman in Berlin suddenly felt qualified to debate relativity. You can picture him tugging at his wild hair, muttering as if space-time itself were easier to manage than the public's curiosity. For you, though, the proof of curved space-time is everywhere. You feel it each time you lean into the ground, each time your coffee mug clings to the table instead of drifting away. Even your own body bends space-time ever so slightly. Technically, the Earth is wobbling around the Sun, and the Sun itself drags the fabric of the galaxy into swirls. You're caught in a cosmic dance choreographed by geometry itself. You stop walking and glance around this trampoline world. In the distance, a massive sphere, let's say Jupiter, presses down so hard that nearby marbles spiral inward. You notice one marble fall straight into the pit and vanish. That's the beginning of a black hole, but you'll stroll closer to that drama later. For now, it's enough to feel how everyday weight is simply geometry under your shoes. Galileo had a hint of this centuries earlier, when he noticed that objects of different masses fall at the same rate. Whether it was cannonballs or feathers in a vacuum, the acceleration was identical. To Newton, this was just gravity's consistent tug. To Einstein, it meant something deeper. Free fall is indistinguishable from weightlessness. When you're falling, you're not experiencing a force, you're just following space-time's curved path as naturally as a marble on a slope. Quirky side note, during World War II, pilots sometimes joked that gravity is a myth. The Earth just sucks. It's a crude but oddly accurate take on Einstein's view. You're not being pulled, you're sliding along the geometry toward Earth's centre. Not very poetic, but memorable enough for a drowsy grin. And here you are, realising the same thing as you sway gently in this imagined field. You're not pinned to the Earth by some magical string, you're gliding along the dent in space-time made by our planet's bulk. Your body feels heavy, sure, but only because the floor is pushing back against your attempt to follow that curve. The weight you feel is resistance, not a pull. You glance up at the stars, at photons that also follow these curves, bending around massive objects, slipping across the cosmic trampoline without complaint. Light itself, once thought untouchable, plays by the same rules you do. Space-time makes no exceptions, whether you're an apple, a satellite, or a starbeam cutting through the dark. And as you take another step, the floor ripples like taut fabric under your heel, whispering a reminder: gravity isn't a force you can hold or see. It's the stage itself flexing beneath your every move. You keep wandering across the soft curved floor of space-time, and soon you stumble into a strange little campsite. Two tents stand side by side, both glowing faintly with lamplight. In one, a twin snores contentedly. In the other, another twin's lacing up boots, ready for an impossible journey. You realise you've walked into the famous thought experiment, the twin paradox. It starts simply. Imagine you and your sibling are born at the same moment, both clutching identical watches. One of you decides to stay home, binge-watching whatever show has replaced sitcoms in the future. The other straps into a rocket, cranks the throttle, and speeds off near light speed. For the travelling twin, time slows down. Their heartbeats, their aging, their Netflix binges, all stretched compared to the homebody twin. When the rocket finally returns, the traveller steps out younger than their sibling. Same birthday, different ages. Spacetime does not apologize. Historically, this paradox puzzled even early adopters of relativity. Some critics waved it around like a smoking gun. See, Einstein's theory makes nonsense. But careful math shows it isn't nonsense at all. The key is acceleration. The travelling twin must turn around at some point, breaking the perfect symmetry of motion. That brief jolt makes all the difference, tipping the balance so their clock really does record fewer ticks. Historians still argue whether Einstein himself explained it clearly enough in his papers, or left later physicists to tidy up the mess. On the quirky side, the paradox has become a pop culture darling. Cartoon shows, sci-fi novels, even late-night comedians toss it around as shorthand for space travel is weird. There's even a joke about twin sisters where one rockets away and returns younger, only to discover her earthbound sibling has spent the extra years learning how to win every family argument. Time dilation, the ultimate sibling rivalry handicap. You wander between the two tents, peeking in at each twin. One has aged into wrinkles and silver hair, sipping tea by the fire. The other bounds out of the rocket, still youthful, still eager, carrying only a few years of memory. Their reunion is awkward, tender and surreal. You realise that the paradox isn't just math. It's a human story about separation, longing, and the unfair bargain space-time forces upon us. Galileo's early musings on relativity, the idea that you can't tell whether you're moving soothly without outside reference, echo faintly here. He imagined sailors below deck dropping balls and watching them fall straight down, whether the ship was at rest or gliding steadily across the sea. That's relativity in embryo, but add acceleration and near light speeds, and suddenly Galileo's sailors are dealing with time warps. Historians still argue whether his little ship-thought experiment planted a seed that blossomed centuries later into Einstein's rocket paradox. You sit by the campfire yourself, watching the twins embrace. Their watches disagree, yet their hearts still beat in unison, and you feel the strangeness of it seep into your bones. Time is not an impartial referee. It favours some paths over others, handing out minutes unevenly, like a sleepy dealer with a crooked deck of cards. Then you chuckle softly at the absurdity. If your sibling really did blast off and come back younger, you could lord it over them. Ha! I aged gracefully while you skipped all the boring parts. Or maybe they'd tease you instead. Ha! I stayed young while you trudged through decades of taxes and laundry. Either way, space-time wins because it keeps the joke running forever. You glance again at the glowing tents. One twin settles into bed, exhausted by years. The other lingers by the rocket, still restless, still glowing with youth. You realise that both are you in a way. Part of you stays grounded. Part of you always yearns to leap across the stars. And space-time, that sly trickster, ensures the two halves never quite meet on equal terms. You wander beyond the campsite of mismatched twins, following a winding trail, dips and sways beneath your feet. The path itself seems to curve where nothing visible bends, as if you were walking across the surface of a giant balloon. This is spacetime's next lesson. Curvature you can't actually see but can feel in every step and every orbit. You pause to imagine an ant crawling across a ball. To the ant, the world looks flat, endless in all directions, until it stumbles into a circle and realizes it's been looping the whole time. You, standing outside, can see the curve easily, but the ant lives inside the illusion. That's your relationship with space-time. You can't float outside the universe to glimpse its true shape. You only infer the bending from how objects move and how light swerves. Historically, the idea of curved space wasn't Einstein's alone. Mathematicians like Gauss and Riemann in the 19th century had already been tinkering with the notion of non-Euclidean geometry, spaces where parallel lines eventually meet or triangles don't add up to 180 degrees. These ideas were playground curiosities for mathematicians at first, like doodles in the margins of reality. Then Einstein grabbed those doodles and said, "Perfect, this is what gravity looks like." Historians still argue whether Riemann ever suspected his abstract lectures would one day describe planets circling stars. On the quirky side, surveyors in Gauss's day actually tried measuring massive triangles made of mountaintops to see if Earth's surface showed curvature in its geometry. Spoiler, it did. Not a shock, but it was a neat way of proving that geometry is tied to the surface you're standing on. You can imagine those poor surveyors shivering in the wind on mountain peaks, scratching numbers in notebooks while thinking, well, at least our triangles are famous now. As you stroll, the ground rolls subtly like a wave, and you notice how your balance shifts. You realise that's exactly what Earth does to space-time. Just enough curvature to keep the moon circling endlessly. If you were to draw the path of satellites in orbit, they'd appear like marbles looping across invisible curves, sliding along tracks you'll never see but always trust. Think back to Columbus sailing across the Atlantic. He believed he was heading for Asia, but he also believed Earth was a sphere. That's mainstream history. But here's the quirky debate. Historians still argue whether the flat Earth myth of his opponents was real or invented later as propaganda. What matters for you is that humans have long wrestled with the shape of their world, and now you wrestle with the shape of the universe itself. Flat, curved, finite but unbounded. You glance upward, where starlight bends gently around the sun, not because the star has moved, but because space between you and it is curved. That bending lets astronomers use gravitational lenses, where entire galaxies act like magnifying glasses, showing distant, hidden galaxies behind them. It's as though space-time itself is helping you peek over cosmic shoulders, offering you a blurry but wondrous view. Closer to home, even the humble GPS in your phone relies on accounting for curvature. Without correcting for Earth's warped space-time, your navigation would slide wildly off course. You might set out for a taco truck and wind up at a tyre shop. Einstein doesn't just haunt your textbooks, he haunts your lunch plans. You stop walking and press your hand to the invisible ground, trying to feel its slope. You know you can't. Your senses aren't built to detect geometry on that scale, but you feel it indirectly when your stomach dips on a plane, when your coffee arcs slightly as you accelerate, when the moon rises faithfully where geometry insists it should. The world is full of clues that you're walking not on flat nothingness, but on folded, bent, gently undulating space-time. And as you lie down, gazing at the imagined balloon's surface sky, you think, maybe being the ant isn't so bad. You don't need to see the curve to trust it. You just follow the paths space-time lays down for you, like a child tracing the ridges of a seashell without ever glimpsing the ocean that shaped it. You rise from the balloon-like ground and find yourself drawn toward a dark horizon ahead, a place where the air grows heavy and sound seems to dissolve into silence. The trail ends abruptly at a yawning chasm, not jagged like a canyon, but smooth, perfect, almost polite. This is no ordinary pit, it's a black hole, space-time pinched into a pinhole so steep that not even light can climb back out. You edge closer, half curious, half terrified, like a moth hovering near a candle flame. Here the rules you've been following buckle. The smooth trampoline of space-time dips until it folds inward, forming an event horizon, the ultimate do not cross line. Step past it and every possible path carries you deeper, never back. The geometry you met in earlier sections, playful and curving, now becomes merciless. Historically, the first hints of black holes trace back to the 18th century. John Michel, a clergyman with a taste for astronomy, wondered whether a star could be so massive that light itself couldn't escape its pull. He didn't call it a black hole, of course, that name came much later, but the seed was there. Einstein's own equations in 15 permitted such monsters, though he doubted they existed in reality. Historians still argue whether he dismissed them because the math felt too strange, or because he simply hoped nature wouldn't be so cruel. On the quirky side, early critics mockingly called them frozen stars, as if the universe had left lumps of burnt toast scattered across space. It wasn't until the 60s that physicist John Wheeler popularised the term black hole, a phrase that stuck partly because it was blunt and slightly scandalous. Imagine being at a physics conference when someone first said it aloud, half the audience intrigued, half giggling nervously. You lean forward and toss a pebble toward the edge. From your perspective, it slows, redshifts, and seems to freeze just above the horizon. To someone falling with it, though, the plunge is swift and final. This paradoxical view is space-time's way of protecting its secrets. Outsiders never see the crossing, insiders never report back. It's the ultimate one-way ticket. Consider the strange way time behaves here. The closer you creep to the event horizon, the slower your clock ticks relative to the universe outside. Stay long enough and you'd witness the distant cosmos speeding up, galaxies aging and fading while you barely sip your tea. Historians still argue whether Einstein ever truly grasped this mind-bending time effect near singularities, or whether later physicists like Oppenheimer and Snyder were the first to follow the math into that abyss. You chuckle softly at the absurdity. Somewhere in the cosmos, black holes are colliding, sending ripples of space-time, gravitational waves rolling outward. Those waves were actually detected in 2015 by LIGO. Faint shivers in reality caught by laser beams, and here you are, daydreaming on your pillow, casually imagining yourself tossing rocks at one. If you lean too far, you know what happens. The black hole swallows you, stretching you like spaghetti in a process charmingly nicknamed spaghettification. Scientists coined the term with a wink, as though dark humour could soften the horror. Quirky fact, the Milky Way harbours a supermassive black hole at its centre called Sagittarius A. If you squint at the right radio images, you can almost picture it smirking at you from 26,000 light-years away, saying, "Come closer if you dare, you dare." And yet, despite their terrifying appetite, black holes might also be creative. Some theories suggest they help shape galaxies, stirring star formation through their violent outbursts. Like cosmic gardeners, they prune and fertilize with jets of energy, even as they hoard matter in their invisible cores. Spacetime isn't just cruel here, it's oddly productive. You step back from the horizon, heart fluttering, and glance again at the smooth pit that seems bottomless. You know you won't cross it tonight, not in dreams, not in rockets, not in thought experiments. But its presence lingers like a shadow at the edge of a campfire, a reminder that space-time isn't just curved, it can collapse, pinch, and guard its mysteries behind a silent wall. You retreat from the black hole's silent maw, and almost immediately the ground beneath your feet begins to stretch. Not sink, not ripple, stretch. Imagine the very fabric of space-time tugged outward like dough ears being kneaded, carrying you and every star, planet, and speck of dust along for the ride. This is cosmic expansion, the universe's quiet trick of growing larger without anything moving through it. Galaxies drift apart not because they're speeding through empty space, but because the space itself between them is inflating. You picture raisins in rising bread dough, each one carried farther from its neighbours as the dough puffs up in the oven. You're not one raisin chasing another. Your seat is glued to the dough, and the dough itself is changing. It's a homely analogy, yes, but one of the best ways to picture why galaxies don't feel any wind in their faces as they move apart. The fabric itself is expanding. Historically, this discovery is tied to Edwin Hubble in the 1920s, who observed that distant galaxies were redshifted, their light stretched toward longer wavelengths. The farther away a galaxy was, the more it was shifted, as if the universe were politely colour-coding distance for us. This was the first strong evidence that space-time itself was expanding. Historians still argue whether Belgian priest Georges Lemaitre, who published the theory of a primeval atom before Hubble's data, deserves more credit as the true father of the Big Bang. On the quirky side, Einstein initially introduced a cosmological constant into his equations to keep the universe static, because he couldn't imagine it changing size. When Hubble's data revealed expansion, Einstein reportedly called his constant the biggest blunder of his life. Ironically, modern cosmologists brought it back in the form of dark energy, so maybe the blunder was just premature genius. You can almost hear space-time chuckling at the long-running joke. You stroll across this swelling terrain, and suddenly the horizon seems farther away than it was a moment ago. Galaxies you imagined close now appear distant, not because they've fled, but because the stage has grown larger under your feet. At small scales, inside the Milky Way, inside your living room, gravity clings tight enough to resist expansion. But step back to cosmic scales, and the stretching becomes undeniable. Consider this. The expansion isn't slowing down. Observations of distant supernovae in the 90s revealed the universe is actually accelerating, as if some unseen hand were turning up the speed dial. That hand is what scientists call dark energy, which frankly is just a fancy way of saying, we have no idea. Historians still argue whether this acceleration was the most surprising discovery of the century, or just another twist in space-time's endless comedy of errors. And here's your quirky bedtime image. As space expands, it stretches not just galaxies, but the very wavelengths of light travelling through it. A photon born blue near a quasar billions of years ago arrives at your telescope blushed into red, like a cosmic traveller whose outfit faded during the trip. It didn't lose speed, it just had its stripes pulled wider by the expanding fabric. You pause, gazing outward. Somewhere far enough away, galaxies are receding so quickly that their light will never reach you no matter how long you wait. They slip beyond a cosmic horizon, forever inaccessible. It's not that they're moving faster than light. It's that space-time itself is stretching too quickly for their photons to bridge the gap. You realize with a shiver that the observable universe is just a bubble in a much larger loaf, and you'll never taste the rest. Quirky fact, astronomers sometimes nickname this future isolation the cosmic loneliness. Billions of years from now, distant galaxies will slip so far away that only our local group will remain visible. Future stargazers might think the universe is static and empty, blissfully unaware of the expansion we measure today. Space-time doesn't just bend your body, it edits your view of history itself. And as you stand there, breathing slowly, you picture the fabric still tugging outward beneath you. Expansion isn't violent. You don't feel yourself stretch like taffy, but it's relentless. The universe is quietly, instantly reminding you that nothing stays fixed forever, not even the stage on which all of existence plays. You step away from the swelling loaf of space-time and into what at first seems like pure emptiness. A dark, silent void stretches all around. No galaxies in sight, no stars flickering. But then you notice it. The air here isn't still at all. It flickers faintly, like static on an old television screen. Empty space, you realize, is anything but empty. This is the quantum foam, the jittery undercurrent of space-time itself. The vacuum, that supposedly quiet stage, buzzes with activity. Virtual particles pop in and out of existence, borrowing energy from nowhere and returning it just as quickly, like mischievous children sneaking cookies before anyone notices. To your sleepy mind, it's unsettling. Even when you think you've found calm, space-time insists on humming beneath you, restless as a fridge at 3 a.m. Historically, the first hints of this quantum jitter came in the early 20th century, when physicists realized that even the lowest energy state of a field couldn't be perfectly still. Zero-point energy, they called it, the unavoidable wiggle left over even when everything else is stripped away. In 1948, Dutch physicist Hendrik Casimir proposed a clever test. Place 2 metal plates close together in a vacuum. If the vacuum truly buzzed with fluctuations, the plates should feel a subtle push inward. Sure enough, experiments later confirmed it. Historians still argue whether Casimir expected his quirky idea to become one of the strangest demonstrations of spacetime's hidden restlessness. Quirky fact, the Casimir effect is so delicate that scientists joke about it being a quantum nudge. The force is tiny, but engineers even wonder if it could someday be harnessed in nanomachines. Imagine a watch powered not by a battery, but by the jittery background hum of space-time itself. Not great for your electric bill, but charmingly futuristic. As you drift in this flickering void, you realize quantum mechanics and relativity don't always play nicely together. Space-time, so smooth and elegant in Einstein's hands, becomes grainy and chaotic under quantum scrutiny. It's like discovering that the perfect silk sheet you admired earlier is, up close, fraying with restless threads. Physicists still debate how to reconcile these two visions. Is space-time continuous or granular? Is it fundamental or emergent from something deeper? The void around you sparkles with brief flashes, particles pairing up and cancelling out. It feels alive, though no sound escapes. You imagine sticking out your hand and brushing against one of these fleeting apparitions, but it vanishes before you even finish the thought. The universe is teasing you, offering glimpses without permanence. Even cosmic expansion ties into this jitter. The mysterious dark energy driving galaxies apart might be linked to vacuum energy. But here's the kicker. When physicists calculate how much energy the quantum vacuum should have, the number comes out absurdly huge. So huge, it would blow the universe apart instantly. Yet the observed value is tiny, a mismatch of about 20 orders of magnitude. Historians still argue whether this is the greatest calculation blunder in physics, or simply proof that we're missing a deeper layer of reality. You chuckle softly at the absurdity. Imagine ordering a coffee and being charged either $3 or $3 trillion, depending on whose math you believe. That's essentially the vacuum energy problem. And yet somehow the cosmos doesn't implode, and your tea still cools at the same pace. You let yourself sink into this flickering emptiness, lulled by the idea that even silence is busy. Space is never truly blank, it's a restless canvas, painted and erased in infinite cycles every second. You think about how comforting that is. Even the loneliest stretches of the cosmos are never truly alone. And as your eyes grow heavy, you realize you're not floating in nothingness at all. You're adrift in a sea of jitter, carried on the ripples of spacetime's quantum heartbeat. The void hums like a lullaby, reminding you that emptiness too is part of the grand design. You drift deeper into the flickering quantum certain sea, and suddenly the scenery begins to shrink around you. Not in the sense that you're getting bigger, but as though your measuring stick is dissolving. Numbers blur, rulers melt, clocks sputter. You've reached the edge of what physics can meaningfully describe, the Planck scale, the ultimate basement level of spacetime. Here, distances are so tiny, about 10 35 meters, that even the word tiny sounds comically inadequate. If an atom were blown up to the size of the observable universe, the Planck length would still be smaller than a tree in your backyard compared to that cosmic scale. At these depths, space and time don't behave like smooth surfaces anymore. They jitter, foam, and perhaps lose meaning entirely. Historically, this scale was first identified by Max Planck in 18 before relativity or quantum mechanics had fully blossomed. He combined fundamental constants, Newton's gravitational constant, the speed of light, and his own quantum constant to cook up natural units for length, time, and mass. They were curiosities at the time, just strange little numbers. But decades later, physicists realized these numbers mark the frontier where our current theories collapse. Historians still argue whether Planck himself foresaw the significance or merely thought of them as mathematical playthings. On the quirky side, some physicists joke that the Planck length is the pixel size of the universe, as though reality were running on a cosmic screen with finite resolution. Zoom in closer and you just get blur no matter how good your microscope. Others go further and say space-time itself might be a kind of hologram projected from an even deeper layer of information. It's both terrifying and comforting to imagine you're a character rendered in high definition, but not infinitely high definition. You try to picture yourself standing on this scale. The ground is no longer ground, it quivers and shreds into frothy uncertainty. Distances lose coherence like lines sketched on water. Clocks tick in fits and starts, unable to settle on steady beats. The universe here is a strobe light, flashing possibilities without permanence. Think of Galileo again, fiddling with ramps and balls to measure time. Now imagine handing him a ruler calibrated in Planck lengths. He'd laugh, shrug, and probably use it as a bookmark instead. You chuckle at the thought, but the point is sharp. Our intuitive sense of measurement fails utterly here. Historians still argue whether any future experiment will ever truly probe these scales or if they'll forever remain abstract boundaries whispered in textbooks. You pause, squinting into the foam. Maybe strings vibrate here, tinier than atoms, weaving space-time like music. Maybe loops of geometry flash in and out, forming a quantum network. Or maybe the whole idea of space and time just dissolve, replaced by something you don't yet have words for. Your mind stretches, then retreats, recognizing that this basement level is built for curiosity, not comfort. A quirky bedtime thought. If the universe really does have a smallest unit of length, then technically you're taller than you think, since your height is measured in a finite number of indivisible steps. Somewhere out there, a cosmic tape measure is rounding you up or down. That's not the kind of thing you'd bring up on a first date, but it's enough to make you smile under the covers, and as you drift in this foamy microcosm, you feel the limits of your perception tugging at your eyelids. Beyond this scale, even imagination hesitates. You don't need to solve it tonight. You just need to rest in the knowledge that space-time has boundaries, not walls to imprison you, but horizons that invite wonder. You step gingerly out of the frothy chaos of the Planck scale, relieved to stand on steadier conceptual ground. Yet just ahead, a peculiar archway glimmers, a tunnel with no visible end, its walls shimmering as though woven from stretched glass. You know what this is, or at least what stories claim it to be: a wormhole, a shortcut through space-time, equal parts physics and science fiction. A wormhole is the idea that two distant points in the universe might be connected by a tunnel, a kind of hidden hallway carved through the fabric. Instead of trekking across galaxies the long way, you'd step through and pop out somewhere impossibly far away, as though space-time had whispered, "Here, take this back door." The concept emerges naturally from Einstein's equations, though whether nature ever builds them is another question entirely. Historically, the first solutions resembling wormholes appeared in 1935, when Einstein and his collaborator Nathan Rosen described what came to be known as the Einstein-Rosen bridge. To them, it was a mathematical curiosity, a link between two black holes, but it was the kind of curiosity that launched decades of speculation in physics and fiction alike. Historians still argue whether Einstein intended anyone to take it seriously, or if he thought of it merely as a footnote in the grander relativity story. On the quirky side, wormholes have been drafted into every corner of pop culture, from time-travelling police boxes to interstellar highways. There's even a theoretical twist. Some physicists muse that tiny wormholes might pop in and out of existence at quantum scales, like cosmic trapdoors appearing and vanishing faster than you can blink. If that's true, the universe is riddled with shortcuts too small for you to ever notice. Spacetime may be far more playful than you thought. You approach the glowing tunnel and peek inside. The walls shimmer like liquid mirrors, curving and stretching away. If you step through, where would you emerge? Another galaxy? Another time? Maybe just the other side of your bedroom? The ambiguity is part of the charm. But there's a catch. There's always a catch. Wormholes are unstable. Left alone, they collapse too quickly to be useful, snapping shut like cosmic mousetraps. Some theorists suggest exotic matter, stuff with negative energy density, could hold them open. Ordinary matter won't do. You would need something we've never seen. Historians still argue whether this requirement makes wormholes forever fantasy, or whether nature has a trick up her sleeve we just haven't glimpsed yet. You smile at the irony. The universe may offer doorways, but then demands impossible keys. It's like space-time teasing you with a dream house, but leaving it locked behind an imaginary fence. A quirky bedtime image. Imagine ordering a pizza, then realizing the delivery person could use a wormhole to arrive instantly from the other side of town. Toppings still hot, crust still crisp. Sadly, no wormholes exist in your neighborhood, at least none stable enough to trust with mozzarella. Still, the thought lingers. You picture civilizations in some distant corner of the cosmos, perhaps clever enough to tame exotic matter, stringing wormholes like subway lines between stars. You imagine postcards reading, "Greetings from Andromeda, trip only 5 minutes." Whether that's fantasy or possibility, space-time keeps the secret tucked away. You step back from the archway, letting it shimmer and fade into the darkness. You don't need to walk through tonight. It's enough to know that space-time's geometry leaves room for shortcuts, doorways, and playful tunnels. Even if they're never built, the mere hint reminds you the fabric is stranger than you can picture, and always ready to surprise you. You leave the glimmering wormhole arch behind, and soon the air around you feels heavier, slower, almost sticky. The landscape doesn't shift much, it just seems to resist your motion, as though space-time itself were sighing. You realize you've wandered into one of its most mysterious features, the arrow of time. Unlike space, which lets you wander forward or backward without fuss, time has a stubborn one-way rule. You wake up, you age, your tea cools. You don't wake younger, you don't watch steam leap from a mug back into boiling water, and you certainly don't find shattered plates leaping back onto shelves. But why not? The laws of physics work perfectly well in reverse. Equations don't mind if you flip the sign of time, yet in lived experience, time marches on, steady and irreversible. Historically, this question has haunted scientists since the 19th century. Ludwig Boltzmann, a pioneer of statistical mechanics, argued that the arrow of time emerges from probability. Systems naturally drift from order to disorder, from tidy to messy. Drop a sugar cube in tea and it dissolves. The reverse, sugar spontaneously reforming, isn't impossible, just so improbable it may as well never happen. Historians still argue whether Boltzmann's ideas were universally accepted in his lifetime, or whether his contemporaries dismissed them as philosophical hand-waving. On the quirky side, there are thought experiments about reverse time universes, cosmoses where entropy decreases, where eggs uncrack and children shrink into infants. Physicists joke about what conversations in such a universe would sound like. "Hello, I'll never meet you again, yesterday." Space-time seems to enjoy tormenting us with the idea that its rules could allow such nonsense, even if our corner of reality refuses. You pause, pick up an imaginary mug of tea, and watch it steam in the cool air. You know without doubt the steam will dissipate, never recondense neatly in the cup. The direction of time is stitched into the way disorder increases, and yet, in the ticking of clocks and the beating of your heart, you feel how personal this arrow becomes. Time isn't just a feature of physics, it's the measure of your own life, pulling you gently along. Quirky bedtime thought. Some physicists argue the entire universe could one day reach heat death, a state where all usable energy is spread evenly, No gradients left to drive processes, no tea to cool because everything is already lukewarm. Historians still argue whether this is inevitable, or whether cosmic expansion might provide loopholes. Either way, it's not a bedtime story to tell small children. But tonight, the arrow feels less ominous and more like a lullaby. Its steady forward march gives you structure, rhythm, the comfort of before and after. Without it, memory itself would crumble. You'd never know if you'd already fallen asleep or were about to. The arrow may be relentless, but it is also merciful. It keeps your story coherent. You lie back and imagine the stars above, each one burning, each one drifting toward its eventual quiet. The universe hums onward, entropy increasing, disorder rising, yet beauty unfolding at every step. The arrow is not cruel, it's simply steady. It tells you, savor the warmth of your tea now because the cooling is part of the experience. And as your eyes close halfway, you let that steadiness soothe you. Time may only march forward, but that's exactly why rest feels sweet, because every moment is unique, unrepeatable, and worth sinking into as it passes. You linger beneath the stars, still mulling over that one-way arrow, and soon the air around you seems to ripple with a quieter theme: disorder. Everywhere you look, patterns unravel. A neat stack of leaves drifts into chaos on the breeze, your footprints blur into the sand, and even the constellations overhead remind you that stars slowly wander from their tidy alignments. This is entropy, spacetime's quiet insistence that order dissolves into mess, and mess rarely climbs back into order. At first glance, entropy feels like an accountant's term, dry and lifeless. But here, under spacetime's watchful gaze, it becomes poetic. Every cooling cup of tea, every melting ice cube, every forgotten laundry pile is part of the same deep rhythm, the universe keeping its books balanced. Historically, the connection between entropy and time was crystallized in the 19th century. Rudolf Clausius coined the word entropy to capture the way energy disperses, and Boltzmann, with his statistical genius, etched the concept into physics forever. His famous formula, SLK log W, still marks his gravestone. It describes how systems evolve toward the arrangements with the most possible microstates, the most ways to shuffle themselves. Historians still argue whether Boltzmann's peers fully appreciated the depth of this insight, or whether his equations were dismissed until later generations made sense of them. On the quirky side, there's Maxwell's demon, a mischievous imaginary creature dreamed up in 1807. The demon stands guard at a door between two chambers of gas, letting only fast molecules through one way and slow molecules through the other, seemingly decreasing entropy and breaking the second law of thermodynamics. For decades, the physicists debated whether such a trick could work. Eventually, they realized the demon would expend energy processing information, paying entropy's toll anyway. Spacetime, smug as ever, refuses loopholes. You walk through the drifting leaves, realizing entropy isn't just an abstract law, it's woven into the fabric of spacetime. Black holes, for instance, famously have entropy proportional to the area of their event horizons. Stephen Hawking revealed they even radiate faint heat, slowly evaporating over inconceivably long times. In other words, black holes are not silent voids. They're thermodynamic furnaces. Historians still argue whether Hawking's insight was the single greatest leap in understanding spacetime since Einstein, or whether it's merely a stepping stone towards something deeper. Closer to home, entropy shapes your own existence. Your body constantly burns energy, dispersing order into warmth. Every breath, every heartbeat, every blink of an eye is powered by entropy's steady increase. It's why you tire, why you slumber, why you sleep, why you age. Disorder isn't your enemy, it's the very current that carries you. And yet entropy is strangely comforting. It tells you why memories face backward, not forward. It tells you why the future feels uncertain and the past feels fixed. It explains why your tea cools, but never reheats itself spontaneously. Without it, there'd be no arrow to guide you, no rhythm to anchor you, no sense of before and after. You pause, looking at a pile of sand where a neat tower once stood. Entropy leveled it, but in doing so, it left room for new towers, new shapes. Disorder isn't just decay, it's possibility. The universe drifts toward mess, but in the drifting, patterns emerge. Galaxies swirl, life arises, stories unfold. Quirky bedtime thought. Somewhere out there, in the mathematical jungle of probabilities, the reverse might happen. An egg might uncrack, a sugar cube might reform. It's not forbidden, just absurdly unlikely. Historians still argue whether rare, spontaneous dips in entropy could ever play a role in cosmology. For you, though, the thought is enough to make you grin sleepily. Somewhere maybe an egg is fixing itself for breakfast. You stretch out, listening to the soft hum of disorder all around. Entropy isn't here to scare you. It's here to remind you that life is change, and change is natural. The universe is unraveling, yes, but unraveling into something vast, intricate, and worth drifting into as you fall asleep. You rise slowly from the sandy swirl of entropy and find yourself wandering into a gallery of mirrors. Each surface gleams with frozen moments, a child's laughter, a candle just lit, a star collapsing, a wave breaking on some distant alien shore. You reach out to touch one mirror and realize none of them are moving. The past, the present, the future, they all seem displayed at once. This is the eerie landscape of the block universe. In this view, time doesn't flow at all. Instead, all events, what you call past, what you call future, exist equally, stitched into space-time like pages in a book. You walking through are simply flipping the pages in order, but the book itself is already complete. To many physicists, this is the logical outcome of relativity. If all observers have their own slices of now, then perhaps all slices exist side by side. Historically, this perspective traces back to Hermann Minkowski, Einstein's former teacher, who in 2008 reformulated relativity into the four-dimensional space-time framework. Minkowski famously said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows." Historians still argue whether Einstein fully embraced the block universe idea or kept his distance from the philosophical implications. He once consoled a grieving friend by saying that the distinction between past, present, and future is only a stubbornly persistent illusion. Was he comforting or confessing? The debate lingers. On the quirky side, philosophers have nicknamed the block universe eternalism, which sounds like a perfume brand. They contrast it with presentism, the belief that only the present is real, and growing block theory, where the past and present exist but the future hasn't yet arrived. Academic conferences sometimes resemble a surreal family argument. Do you live in a block, a growing block, or just a fleeting present? You wander deeper into the gallery, mirrors stretching endlessly. In one you see yourself as a child, in another as your older self, in another not yet born. They all shimmer simultaneously, indifferent to which one you think is now. The unsettling part is realizing your sense of flowing time might just be your brain moving along one fixed path in space-time, like a needle tracing grooves in a record. Quirky bedtime thought. In the block universe, your embarrassing middle school haircut is still out there, just as real as this moment. You can't escape it. Somewhere in space-time it is eternally Tuesday, eternally awkward, eternally captured. Comforting? Maybe not. But at least your better hair days are eternal too. And yet the block universe isn't universally accepted. Many physicists argue it strips away the dynamism of time, turning the living cosmos into a static sculpture. Others counter that the flow of time is an emergent phenomenon, not fundamental. Historians still argue whether the block view is science, philosophy, or a mix of both. You pause before one mirror showing a sunrise, the light frozen just above the horizon. It's beautiful, but also still. If this is reality, then every sunrise that ever happened, and will happen, is already etched into space-time. You don't experience them all at once, but they exist nonetheless. And so you wander through this gallery, a little unnerved, but also oddly soothed. Maybe time doesn't flow, but your story does. Maybe you're not writing the book as you go, but reading a book already finished. Either way, the pages are there, waiting for your eyes to drift over them. You step carefully out of the mirror gallery, the frozen scenes fading into mist behind you. Ahead, the landscape grows stranger, less like a solid stage and more like a whispered rumour. You realise you've entered the realm of speculation, where some physicists argue space-time itself may not be fundamental at all. Perhaps it's not the bedrock of reality, but something that emerges, like frost patterns on a window pane or ripples on water. Imagine stirring cream into coffee. The swirls appear beautiful and complex, but they're not basic, they're the result of deeper, simpler motions beneath. In the same way, space-time might be the swirl, not the cream. The real ingredients could be hidden entities, quantum bits, or entangled information, with space-time arising only as their collective illusion. Historically, this idea began to sprout in the late 20th century, as physicists struggled to reconcile Einstein's smooth fabric with quantum mechanics' jittery rules. Black hole thermodynamics hinted at something deeper: entropy encoded on horizons, surface areas storing information like cosmic hard drives. Jacob Bekenstein and Stephen Hawking pushed this frontier, showing that black holes have entropy and temperature as though they were made of invisible microstates. Historians still argue whether those discoveries were the first true cracks in spacetime's solidity, or just clever add-ons to relativity. On the quirky side, some researchers toy with the idea that spacetime could be woven from quantum entanglement itself. Imagine tiny threads of connection, invisible but real, binding particles across distance. Enough entanglement, and a geometry emerges, like friendship networks forming a city map. In this view, you don't live in space-time. You live in an enormous web of relationships, and the stage is just the byproduct. Quirky bedtime thought: you're less like an actor on a stage and more like a node in the universe's cosmic group chat. You stroll across this new terrain, and the ground feels uncertain, as though it might dissolve if you stare too hard. You wonder if this is what physicists mean when they talk about emergent space-time. It's not a thing but a story, written by deeper laws that you can't quite glimpse. The comforting image of space-time as a sturdy fabric begins to blur, replaced by something more fragile, more ephemeral. Galileo once mused that the universe is written in the language of mathematics, but if space-time itself isn't fundamental, then maybe the language he imagined is only a translation, not the original script. Historians still argue whether Galileo's confidence in eternal mathematical laws holds up in a world where even geometry might be emergent. You pause, sit down on this uncertain ground, and run your hand through the mist. Maybe space-time is like temperature: real, measurable, undeniable, but not fundamental. After all, temperature arises from the motions of countless molecules. No single molecule has it, yet together they do. By that analogy, no single particle has time, but collectively, the cosmos manifests it. The thought makes you laugh softly. For centuries, humans believed space and time were absolute and solid. Then Einstein showed they were flexible. Now, physicists suggest they might not even exist on their own. It's like playing cosmic Jenga, pulling out one assumption after another to see what still stands. And as you lean back into the mist, eyelids heavy, you find comfort in the idea that even if space-time isn't fundamental, it's still the world you move through every day. Whether it's the fabric or just the pattern, it's the dream you're living in, and tonight it's enough to let that dream carry you. You stand from the misty ground and hear a faint vibration, like strings plucked on an unseen harp. The sound is everywhere and nowhere at once, resonating through your bones and rippling through the air. You've wandered into the speculative concert hall of string theory, where physicists imagine that the smallest ingredients of reality aren't particles at all, but tiny vibrating loops. Each loop hums a note, and together their music could weave space-time itself. Picture a violin string. Depending on how it vibrates, it produces different tones. Now shrink that idea trillions of times smaller, down to the Planck length. The same string, vibrating in one mode, might appear to you as an electron. Vibrating differently, it might appear as a photon. Change the rhythm and you get a graviton, the particle that, if it exists, would carry gravity. In this way, the universe becomes a symphony, and matter is just its music. Historically, string theory first appeared in the late 1960s, oddly enough, as an attempt to describe the strong nuclear force. Only later did researchers realize its equations naturally included gravity, hinting at a possible theory of everything. Since then, generations of physicists have wrestled with it, building frameworks like superstring theory and M theory. Historians still argue whether the decades of work represent progress toward truth or an elaborate detour fueled by beautiful mathematics. On the quirky side, string theory demands extra dimensions, sometimes as many as 10 or 11 curled up so tightly you never notice them. Imagine living in a two-dimensional sheet of paper, convinced that's all there is, while unseen folds curl into directions you can't perceive. A quirky bedtime image, somewhere, entire galaxies of ants might be marching through curled-up dimensions inside your bedroom wall, and you'd never know. You wander through the hall of vibrations, each tone shimmering like coloured light. You realise space-time itself might be an emergent harmony, not a stage at all, but the sound of strings resonating together. If so, then asking what is space-time is like asking what is a chord, is not a thing but a pattern. Einstein once hoped for a unified theory that would blend gravity with quantum mechanics. String theory presents itself as a candidate, though critics note it hasn't yet made a single testable prediction. Historians still argue whether Einstein would have embraced its elegance or dismissed it for lacking experimental teeth. You picture him frowning at chalkboards filled with curled dimensions, muttering in German about wasted chalk. You pause to pluck an imaginary string yourself. The vibration hums, faint but resonant, and the space around you seems to shimmer. Perhaps you're not standing in space-time at all, but floating in music, your body just one harmony among many. Quirky thought to take to bed. If reality really is music, then maybe the reason you love songs is that your entire existence is tuned to resonate with them. Each melody is a reminder that deep down, you are literally made of vibrations. The notes around you soften, the hall fades, but the hum tsingekakos lingers in your chest like a heartbeat. You realize that space-time might not be a stage, not even a fabric, but a melody endlessly playing. And tonight, drifting off, you're just another listener carried by the song. The vibrations of the cosmic harp fade, leaving you adrift in a space that feels oddly flat, like the back of a vast screen. Shapes shimmer faintly, as though your world has been reduced to patterns of light and shadow on a surface. You realize you've wandered into one of the strangest modern ideas about space-time, the holographic universe. The suggestion is audacious. What if everything you experience, space-time, the sense of depth and motion, is a kind of projection? Just as a two-dimensional hologram encodes a three-dimensional image, maybe our four-dimensional space-time is encoded on a distant boundary. You lying here in your bed might be more like a cosmic holographic image than a being moving through a solid stage. Historically, this idea grew from the study of black holes in the 1970s and 1980s. Jacob Bekenstein proposed that a black hole's entropy isn't proportional to its volume, but to the area of its event horizon. Stephen Hawking's calculations reinforced this view, suggesting information is stored on surfaces, not in the depths. Later, in the 1990s, Gerard 't Hooft and Leonard Susskind developed the holographic principle, arguing that perhaps all of space-time works this way. Historians still argue whether this principle was a revolution in physics or just a clever metaphor stretched too far. On the quirky side, theorists love pointing out that if you live in a hologram, then in some sense you're flatter than you feel. Your life, your laughter, even your midnight snacks might be encoded on a distant cosmic shell, like a movie playing on an unimaginably vast drive-in screen. Quirky bedtime thought. Somewhere your whole biography could fit neatly on the wallpaper of the universe. You reach out and tap the shimmering screen in front of you. It ripples, and suddenly depth reappears, mountains rising, stars glowing, rivers flowing. Yet part of you wonders, is the depth an illusion, like the trick of a holographic sticker? If so, the real magic isn't the image, but the data etched on the unseen boundary. The holographic principle even connects with string theory. In one famous case, the ADS-CFT correspondence, two entirely different descriptions of reality were shown to be mathematically equivalent. A universe with gravity in a higher dimensional space, and a universe without gravity on a lower dimensional boundary. Historians still argue whether this duality describes our actual cosmos, or just a toy model that happens to be dazzling. You lean back, slightly dizzy. If the universe is holographic, then space-time is not the ultimate stage but the illusion created by deeper information. The question, where are you, becomes slippery. Maybe you're here, maybe you're there, maybe both. And yet the thought is oddly calming. Even if you're a projection, you're a faithful one. The stars still shine, the earth still turns, your pillow is still soft. Whether you're woven into a fabric or printed on a screen, your story feels real. As the shimmering surface fades into the background, you carry the sense that space-time may be more like a film reel than a floor. The beauty isn't in proving it one way or the other, but in realizing that even illusions can cradle you gently as you drift towards sleep. The shimmering screen dissolves, and you step forward into a corridor that seems far too wide, far too empty, and oddly layered. The walls don't just stretch outward, they fold inward, curve around, and vanish into directions you can't even point to. You've stumbled into the realm of extra dimensions, the possibility that space-time is more spacious than the four coordinates you know. For everyday life, you work with 3 dimensions of space and 1 of time. That's enough to find your shoes, bake lasagna, and get lost on road trips. But some theories whisper, What if the universe hides more directions, curled up so tightly you don't notice them? Like hidden hallways tucked behind the wallpaper of reality, they could be there all along, shaping the physics you see without ever letting you step inside. Historically, this idea isn't new. In the 1920s, Theodore Kaluza and Oscar Klein proposed a 5-dimensional theory that unified gravity and electromagnetism. The extra dimension, they suggested, was compactified, rolled up so small it was invisible to human senses. Historians still argue whether Einstein truly supported Kaluza-Klein theory, or politely humoured it while focusing on his own quests. On the quirky side, modern string theory demands not just one extra dimension, but 6 or 7, all curled into fantastical shapes known as Calabi-Yau manifolds. These manifolds are so complex that mathematicians describe them with equations that look like doodles from an alien chalkboard. Quirky bedtime thought: right now you might be lying on a mattress that quietly extends into 7 invisible directions, and your bedsheets could, in theory, loop through a Calabi-Yau cavern without you noticing. You walk down the corridor and feel the tug of unseen directions. It's disorienting, like your body wants to lean sideways into a place your senses refuse to admit exists. You reach out to steady yourself, but your hand slides against air that folds in a way a language can't describe. Even pop culture has toyed with this. Think of science fiction portals or stories about being slipping into higher planes. Those tales may be fanciful, but they echo the serious possibility that your world is just a slice of something bigger. Physicists even speculate that gravity's apparent weakness compared to other forces might be explained by its leakage into extra dimensions. In other words, your trampoline sag may not be confined to your surface. It may echo into unseen spaces. Galileo, with his telescopes, revolutionized your view by revealing moons circling Jupiter. Imagine handing him the idea of 10 dimensions. He'd probably drop his spyglass, sigh, and mutter that the cosmos had gotten entirely out of hand. Historians still argue whether thinkers of his era would have embraced extra dimensions as natural philosophy or dismissed them as absurd fantasy. You pause in the corridor, staring into folds that curl back on themselves. Whether real or not, the idea is strangely comforting. If there are hidden directions, then the universe is even richer than your senses allow. The walls of reality aren't plain. They're embroidered with patterns too small and subtle for you to see. And as you take a slow breath, you let the dizziness pass. You don't need to map these extra hallways tonight. It's enough to know they might exist, carrying whispers of physics beyond your reach, waiting for future dreamers to stumble upon them. You step gently out of the folded corridor, leaving the dizzying extra directions behind, and find yourself back on a familiar stretch of space-time. The ground feels steadier now, like the soft carpet of your own living room. After wandering through curvatures, black holes, quantum jitters, wormholes, and holograms, you've returned to a quieter place, where the question lingers like a lullaby. What does space-time mean to you? You pause and glance back over your journey. You've trudged across to Tusson's absolute grid and Einstein's pliable geometry. You've chased beams of light that refuse to be outrun. You've watched clocks tick unevenly in fields and satellites, felt the sag of gravity under your feet, and peeked nervously into the one-way doorways of black holes. You've floated on cosmic expansion, brushed against quantum foam, and laughed at the absurdity of Planck-sized pixels. You've toyed with wormholes, traced the arrow of time, and learned that entropy is both a trickster and a guide. You've peered into a block universe of frozen moments, questioned whether space-time is fundamental, and listened to the faint music of strings vibrating in higher dimensions. Finally, you've pressed your palm against the shimmering holographic screen and tiptoed through extra hallways curled tighter than any sheet you've ever folded. And yet, for all that wandering, you return here, to this moment, this room, this breath, because space-time isn't just the cosmos at large, it's also the fabric that cradles you in the ordinary. It's why you fall asleep downward and not sideways, why your clock ticks in rhythm with your heartbeat, why the light from your lamp takes a fraction of a nanosecond to kiss your eyes. Here's a quirky thought to soften your pillow. Your body bends space-time ever so slightly. Not much, no galaxies are orbiting you, but enough that if you were alone in the void, space-time would still cradle your mass. In that sense, you're not just in space-time, you're shaping it, leaving your own dent in the universal fabric. A personal signature, however small. Historians still argue whether human culture has kept up with these revelations. For most of history, people lived with the assumption of flat, absolute time and space. The notion that your reality might be curved, emergent, or illusory is still trickling through art, philosophy, and daily life. Maybe one day kids will learn about holographic universes in the same casual way you learned about gravity and rainbows. Or maybe not. Space-time has a habit of staying mysterious. You sink to the ground, close your eyes, and feel it all at once. The expansion tugging galaxies away, the jitter of quantum fields, the hum of strings, the slow nudge of entropy, the unwavering arrow of time. Space-time is not just an answer to where and when, it's the silent rhythm that lets your story unfold at all. And so you let the thoughts settle, gentle as a blanket. You are not separate from space-time, you are space-time, a ripple in its weave, a fleeting but real patterns in the tapestry. That truth, however strange, is also soothing. The stage holds you, the song carries you, the screen projects you, and the fabric wraps you. Now let your eyes close fully. Let space-time cradle you, not as a puzzle to solve, but as a pillow to rest on. Whatever it is, fabric, foam, block, or hologram, it is your home, and tonight it hums you towards sleep. And now, as you drift at the edge of wakefulness, let the pace soften. Imagine the universe as a great ocean stretching quietly in all directions. You're not paddling or struggling in it, you're floating, weightless, carried by currents too broad to notice. Every ripple that seemed sharp and puzzling before now dissolves into a gentle rhythm, steady and slow. The stars above blur into a soft haze. They're no longer pinpoints of fire but lanterns diffused through mist, glowing with patient calm. Time itself feels stretched. Its arrow no longer urgent but lazy, as if even seconds are yawning with you. Every sound fades, the quiet tick of a clock, the distant hum of the night, and folds into silence. You're safe here. The black holes that once threatened, the expansion that once pulled, the entropy that once unsettled, all of it is softened now, tucked away behind the curtain of dreams. What remains is only calm. The knowledge that the cosmos, vast and strange as it is, holds you gently in its weave. Your breaths grow slower, one carrying you deeper into the fabric. Inhale, and the universe expands. Exhale, and the stars draw near. Inhale again, and the galaxies drift wider. Exhale, and you find yourself at home in the smallest corner of space-time, your pillow, your blanket, your body resting. Let your mind dim like a fading lantern. Let the last threads of thought unravel, not with effort but with ease. The story has been told, the questions can wait, and the only task left is to surrender to rest. Good night, traveller of space-time. Sweet dreams.